reshape that area into a rectangle, and a rectangle whose base would still be from A to B. Like, that's theoretically, physically possible, right? It's just some area, and I could reshape it into a rectangle. So if I reshaped this into a rectangle, it might be a rectangle then that looks like this. The base is still the same. But instead of this odd figure, then now I have this rectangle. The height of this rectangle, I'm going to call f of c. And the x value is called c. So some number between a and b, where the height of that perfect rectangle is f of c. What would the area of that rectangle be? B minus a is the base of the rectangle times the height, which is f of c. So f of c times b minus a. F of c is the average value. That's what it says right here. F of c is called the average value of f. If I take this average value, since f of c is the average value, I need to put parentheses here. And that also represents the area. That's the same area represented by the integral in the first part. So if these areas are equal, then I could say the average y value of f times b minus a is equal to the integral from a to b for f of x dx. And then what would I get? How would I solve for the average value here? Divide. So the integral from a to b for f of x dx divided by b minus a. Could I write that division by b minus a as multiplication by 1 over b minus a?
Yes.
And that's what that box is right there. So the average value of f. Okay, so what I will say over and over again for average value, erase that. To find average anything, integrate the anything divide by the interval. Sometimes students say the integral over the interval. The integral over the interval is the average. What we're doing here, if we wanted to find an average grade, then we would sum up all our grades and we divide by the number of grades. That's how you find an average. Well, here we're summing up all the y values and we're dividing by the size of the interval. So essentially we're doing the same thing there as well. So if we want to find average velocity, we integrate velocity, we divide by the interval. If we want to find average temperature, integrate temperature, divide by the interval. If we want to find average anything, we integrate the anything, we divide by the interval. The reason that this is called mean value theorem for integrals, if I want to find the average rate of change, I would integrate the rate of change. What's the rate of change of f? Rate of change meaning what? What is rate? Slope. So what is rate of change of f? How do we represent that? I would integrate the rate of change of f. I would divide by the interval. And what am I going to get when I integrate f prime? F and then I would plug in the upper limit, and I would plug in the lower limit. And there's our formula from the beginning of the year. That's how we found average rate of change at the beginning of the year. We did the change in Y over the change in X. Well, we also did it last year a lot. On almost every test, we found average rate of change by doing the change in Y over the change in X. So here's the average rate of change. Again, a fundamental theorem also, when we integrate a rate of change, we get an amount of change. And then we're dividing that by the size of the interval, and that's giving us an average rate of change. Okay, so let's apply this average rate of change. Here's some graph of f. What's the average value of f? So when I see that average value, if I want to find average anything, I integrate the anything, I divide by the interval. So if I want average value of f, this is from -4 to 4. Then I integrate f, I divide by the interval, top minus bottom. To find average anything, integrate the anything, divide by the interval. To find average value of f, integrate the values of f, divide by the interval. Here's f. How am I going to integrate f? We're going to use area under the curve. We're going to sum up the signed areas. Positive for area above the x-axis. Negative for areas below. And then we're going to divide by the interval. And keep in mind that dividing by the interval is the same as multiplying by the reciprocal of that interval. So we could divide by 8 here. We could also multiply by 1/8. What's the area of that first triangle? 1. This second one is 3. And the last one? It's not a rectangle, but it's a trapezoid. Yeah. So, are you saying could we turn the trapezoid, or not just the trapezoid, but I guess that, and have the area from 2 to 4 be a rectangle and a triangle? Sure. Yeah. Is this, what is that? 2.5? 3.5. And then making sure that we do what here? Subtract the area that's below. Mm-hmm. 1.5 times 1/8. Yeah. So might be better here to write that 1.5 then as a fraction rather than a decimal. 1/8 times 3/2, which is 3/16. And then using that idea of that perfect rectangle, if we drew a rectangle whose base was from -4 to 4, the height of that rectangle would be approximately 1/4, so 3/16, a little bit less than 3/16. Here is that, what they call that, quote, perfect rectangle. Keeping in mind that that area below the curve is going to take away from some of the area above the curve. Mm-hmm. has this color. How's that? Because the idea that we started from was taking that area under a curve and reforming it into this rectangle that had the same base and the same area. And so this is what this rectangle would look like. Here's our average value. The average value being the height of this rectangle that has the same base and the same area as the area between the curve and the x-axis. Keep going? Gonna keep going? Okay, so another function, this one also says find average value. Also with average value, sometimes what people forget to do is divide by the interval, and they don't, I guess, make sense of their answer after the fact that if this is supposed to be the average value, it should represent all the values. And sometimes, like with temperature especially, there will be a bunch of temperature values that are, say, between 200 and 220, and then they'll forget to divide by the interval, and they'll end up with an average temperature of 1,000. Well, if all the temperatures are between 200 and 220, the average temperature can't be 1,000. And if they would have divided by the interval, then they might have ended up with something in the 200s. Kind of like with grades. If all your grades are in the 90s, your average is not going to end up being 70. And if all your grades are in the 70s, your average is not going to end up being a 90. So the average is supposed to be representative of all the numbers. Okay, the next one, here's this function, and we want to find the average value of f. If I want to find average anything, I integrate the anything, I divide by the interval. So if I want to find the average value of f, I'm going to integrate the values of f. And this is the average from 5 to 17. I'm going to divide by the interval. So it's top minus bottom. And instead of dividing by 12, we could also say that we're multiplying by 1/12. So just recognizing those as the same statement. Do we have a function to integrate here? So if I can't find the exact area because I don't have a function to integrate, then we're going to approximate that area, and we're going to approximate that area using a Riemann sum. And this Riemann sum is a left Riemann sum. Some people on the test I think asked for a left Riemann sum. No, it asked for a right Riemann sum. And some people did the left Riemann sum. So it does make a difference. The other thing that people will do on this type of problem is, this is an approximation type problem, is they'll forget about the 1/12. So let's write that first. 1/12, and this is the left Riemann sum with 3 rectangles. What's the width of the first rectangle? And the height we're using? 23. The left endpoint. The second rectangle is 3. And then 29 for that left endpoint. And the last rectangle. And then 36 for the last endpoint. If the question asks for average value, then if it's free response, we could stop here. If it's not free response, then probably the answer is simplified and we would use our calculators, but if it was free response, we could stop here. And if they ask for units on a free response, then we could just write the units at the end. Is that good? You want to calculate this number? No? Okay, let's go on. This problem, half of the problem is on the front and half the problem is on the back. Here's the speed of traffic between 1 and 4, modeled by this function S of t, where t is the hours, number of hours past noon. Compute the average speed. And this says use your calculator, so how would I find average speed? The integral over the interval. Or if I want to find average anything, I integrate the anything, I divide by the interval. So if I want the average speed, I integrate the speed. I divide by the interval. This interval is from what time to what time? 1 to 4. Divided by 4 minus 1, which we could write as 1/3 the integral from 1 to 4 s of t dt. For calculator problems, you need to show your setup. When you show your setup of an integral, it's better to use the function name. This function is named s of t. It's better to use that than to write the explicit function, because if you write an exponent wrong, or you write a minus sign instead of a plus sign, or a plus sign instead of a minus sign, then you lost the points for the setup. So if you copy the problem down wrong, you lost the points for the setup. We're going to integrate this function. Do it. Math 9, yes. Using the calculator. Sorry, no, I couldn't hear you. And then we don't want to forget to multiply by that 1/3. So you can multiply first, or you can multiply afterwards, as long as you do it. What are the units here? Kilometers per hour. So it is a speed. It should have units of speed. If we look at the integral could tell us the units also. We're integrating s of t, which is given in kilometers per hour. We're multiplying s of t times d of t. What are the units for d of t? Time. So times hours. And we're dividing by the interval, which is an interval of time. And so that also would be hours. And so when we cancel hours with hours, we're left with kilometers per hour. Kilometers per hour. Keep going? Questions about that problem? Old AP test problem here. Try this one. This one is a calculator problem also. Ready? Good. It's not. So, all right. Why are you saying it's a second derivative? Right. So, I get what you're saying. So, his question is, are we looking at the second derivative here? Because the question says a twice differentiable function w. What are they telling us when they say a twice differentiable function w? That the second derivative exists. So they're not saying that this is the second derivative. Differentiable means able to be differentiated. And so twice differentiable, able to be differentiated twice. So this is still w, but twice differentiable. So we are wanting to approximate the slope of the tangent. At 12, we're approximating the slope of the tangent using the slope of the secant. And I'm using 9 and 15 because 12 is in the middle of 9 and 15. And then we also need to show the units. They specifically here are saying using correct units. So what we're about to do after this is talk about interpreting, because they often ask us to interpret what's the meaning of this calculus notation. And so we'll talk about a specific structure for how we would interpret. What does W prime represent here? So even looking at the units here, what are the units going to be? Degrees Fahrenheit divided by minutes. So if this is degrees Fahrenheit per minute, then it's a rate of change. It's a derivative, so it's a rate of change of what? Of temperature. Rate of change of temperature. In degrees Fahrenheit per minute. Because it's a different rate of change of temperature. It represents something different if it's in degrees Celsius per hour. So this is the rate of change of temperature in degrees Fahrenheit per minute. And this is at t equals 12 minutes. It's actually not the rate of change, it's the approximate. Because we didn't find the exact, but we found the approximate rate of change. Okay, but that one's not really like what we've been doing. This is average temperature, so 1/20th. This is a left Riemann sum. This is from 0 to 20. So this is 4 times 55. 5 times 57.1. 6 times 61.8. And 5 times 67.9. And then we don't want to forget that 1/20th. Like, do we have a function to integrate? We don't have a function to integrate. So then if I'm going to find the area under this curve or sum up the signed areas under this curve, it's going to have to be an approximation using rectangles. And this is a left-hand approximation. And then if this is free response on the AP test, that's full credit right there. It's the setup and it's the non-simplified answer. Everybody okay with that? And then the last part of this problem says, is this an overestimate or an underestimate? Why is it an underestimate? It's an increasing function and a left Riemann sum. So for an increasing function with a left Riemann sum, the Riemann sum is going to be an under approximation. And that's really what we want right here. W of t is strictly increasing. So the left Riemann sum t. Where did that bucket come? Underestimate. If they ask for units, I don't know if they ask for. If they ask for units, then we definitely should put units. It's average temperature, so then the units would be what Andrew said. The units would be degrees Fahrenheit. And if we wrote the non-simplified answer here, but we wanted to put units, then we could just attach units. Go ahead, Tweet. So this one probably has multiple points attached to it. It's going to have, number one, it's going to have points for the Riemann sum. Then it's going to have points for the correct average value. And then it's going to have points for the underestimate or overestimate with justification. So there's probably 3 points attached to this problem. So number one, do I have the correct left-hand Riemann sum? That's shown right here. And the Riemann sum should look like areas of rectangles added together. So I don't want to do too much work in my head because I want to show the setup and the answer. This is both the setup and the answer, non-simplified answer for the left Riemann sum. Do I also have the non-simplified answer for the average? Well, when I take my left Riemann sum and I multiply it by 1 over 20, then there's also my correct non-simplified answer for the average. So then that's 2 of the points. And then do I have the correct underestimate with explanation, with the correct explanation? And that's where the third point for just part B here, the third point comes from for this true response. What about the last one? Go ahead, Tommy. Since this is, they tell us that WT is a strictly increasing function, and we're doing a left Riemann sum. So the left Riemann sum is going to be an underestimate of what the exact area is. Anybody else? Go ahead, Jason. Not Jason. Sean. It is Sean. Say that again. So a midpoint Riemann sum is going to depend on the shape of the curve and not just on whether the curve is increasing or decreasing. So in that case, what they might ask you is for a trapezoid approximation, whether that's overestimate or underestimate when we're talking about concave up or concave down functions. So for example, here's a concave up function. And if I do a trapezoid approximation, then this trapezoid approximation is an overestimate for this concave up function. And if it's a concave down function, that's not a good picture. If it's a concave down function, then the trapezoid approximation is going to be an underestimate. But probably, I'm guessing just those two. And again, I'm guessing, but I'm pretty sure about it. That if it's a left hand or a right hand, they even had to give us information about WT. They had to tell us that WT was increasing and strictly increasing in order for us to know over approximation or under approximation. Trapezoid approximation, they would have to tell us also whether the function was concave up or concave down. They could tell us that also in terms of the derivative. They could say, in this problem, they could have said W prime is positive and never say that W of t is strictly increasing. But if W prime is always positive, then that means W is always increasing. So I don't think they would ask us about the midpoint Riemann sum because the midpoint Riemann sum, it depends more on the shape of the curve. Everybody get what we would do for the last one? What would we do for the last one? We would graph. How would we find average value? The integral over the interval, so 6 minus negative 1, from negative 1 to 6. Which then is going to be 1/7 the integral from negative 1 to 6. It says without integrating because what it means is without doing the antiderivative. And so how would we do this without doing the antiderivative? We'll find the area, right? So can we skip that part? Anybody opposed to skipping that? Let me ask this: if we were going to, if instead of say this part, if we were going to integrate this piecewise function from -1 to 6, how would we integrate it? You integrate, say that again? So integrate 3 minus x and integrate 2x minus 6. And what are the limits going to be? -1 to 3, 3 to 6, and both of those integrals would have to be multiplied by 1/7. And I think other teachers, they do definite integrals a little bit later. So other teachers, they will probably have to use geometry here, but we have options here. We could use geometry and add sum up the signed areas. These areas are going to be triangles or trapezoids. But we can do antiderivative as well. All right, let's move on.